Hi, this is going to be a quick review of Chapter 12 to get you ready for the Chapter 12 test. Now before I start working some sample problems, let's take a look at the definition of what a logarithmic function is. The log function is given by y equals log base a of x. X has got to be positive and a can't be 1. Now, the thing that you need to remember is that the log function is the inverse of y equals a to the x. So in other words, y equals log base a of x is equivalent to x equals a to the y. This yellow equation right here is the inverse of this equation here that's in green. So what I have in yellow here are equivalent. They're both the inverse of y equals a to the x. Now the working definition that I told you needed to remember and memorize is that the log of a number is the exponent that you put on the base to get that number. So when I look at the keywords here, the log of a number is the exponent that you put on the base to get that number. So the log of a number is the exponent you put on the base to get that number. Remember, the logarithm is always an exponent. Okay, so now let's look at the laws of logs. Now before we look at the properties of logs, I think it would be helpful to just get some more foundational information under our belt. So first of all, when you see a common log, that means it's a base 10 log. So instead of writing log base 10 of a number like 7, we can just write the log of 7. And it's understood that if there's no number written for the base, that it's a 10. Similarly, we have the natural logarithmic function. If you remember f of x equals e to the x is as being an exponential function, remember that e is just a number that's roughly 2.72. The inverse of that would be the log base e of x. So on your calculator, instead of writing the log base e of x, we write ln x. So just remember that ln x is the same as log base e of x. You have a button on your calculator for log, which is base 10, the common log, and ln, which is natural log, with base e. Okay, I want to remind you of what the graph of a log function looks like. What I have graphed first here is y equals 10 to the x. The inverse of that would be y equals log base 10 of x, the common log. So when you have a function and you find the inverse, graphically what that looks like is the reflection over the line y equals x. So let's just look at a couple things about this graph. First of all, the log function will always go through the point 1, 0. Whether it's a log base 10, log base e, or anything else. Because the log of 1 is the exponent you would put on a base to get 1, and so that would have to be 0. So 1, 0 is on the graph. Also, notice that the y-axis acts as an asymptote, so I will never use any x values from 0 to the left. You cannot take the log of a negative number. Okay, here we have the properties of logs. I've listed the general logs on the left with a base a. I could have written just the log with no base at all, and then we would talk about the common log, but these properties are true regardless of the base. So I wrote them with the log, and then I wrote the same ones over here with ln for natural log. Now actually, the first three are the ones that are usually called the laws of logs. That's the product, the quotient, and the power rules. So if you take the log of a product, it becomes the sum of the individual logs. The log of a quotient becomes the difference of the individual logs. And if you have an exponent, if you're taking the log of a number raised to an exponent, the exponent comes down front. Now, these last three, those are just some additional properties that I put on here because sometimes you run into them. For example, if the bases match, the log is 1 because the log of a is the exponent I put on a to get a, so it has to be a 1. Over here, when you see that the base of the log matches the base of the expression, they basically undo each other and you're just left with n. That follows actually from this rule here, because if I took this exponent and put it down front like this, I'd have the log base a of a, which we know is 1, and n times 1 is 1. Over here the same thing. I didn't talk about this one. Remember the graph that I showed you? The log of 1 is always 0 because the exponent that I have to put on the base to get 1 is 0. Over here, the exponent that I have to put on my base to get a is 1. And over here, if I ask what's the exponent that I have to put on the base to get a to the n, well, the answer would be n. So remember that bases are exponents, or excuse me, logs are exponent. So the log is 1, the log is 0, and the log is n. And over here, the natural logs follow the exact same rules. So now that we have that foundation, let's just look at a few sample problems. Alright, we know that the logarithmic function is the inverse of an exponential function, but we also looked at some other types of inverses. For example, if you're given just a set of ordered pairs, the inverse of that is going to be what you get when you simply reverse the x's and y's. So the inverse of this would be 7, 3, 1, 2. If you have an equation, then to find the inverse, you just simply replace the y with an x and the x with a y. Now don't leave it like that, because when we find inverses, we generally will solve for y. So in this case, I would add 8 to both sides, and then I would divide through by 2, and I get y equals 1/2 x plus 4. That would be the inverse. Alright, for something like this, the inverse would be x equals the sine of y. I can't easily solve that for y, so we have our functions called arcsine, arccotangent, arcsecant, and such. So the way that this is going to look when I solve this for y is y equals the arcsine, which might be written this way, arcsine of x, or it might be written as y equals the arcsine of x, written sine with a little -1. When you see this, you need to say, where is the sine x? So this is the inverse of y equals the sine of x. Now, a couple other things about the inverse trig functions I want to go over very quickly. When you consider the function arcsine, which can be written either of these two ways, the answer that you get must be in what I like to call the red zone. If you put it in your calculator, it will give you an answer in the red zone. If you're figuring it out on your own from the unit circle, you must give an answer that's in the red zone. So from -π/2 to π/2. Now for arctan, I'm going to jump over here too because it has the same zone. The calculator will give you an answer in this zone, and if you're doing it by hand, you have to give an answer in this zone. For arccosine, the answer is in a different zone. It's from 0 to 2 pi. So for example, if I ask you for the arcsine of radical 2/2, I'm asking you, where is the sine radical 2/2? Well, you should know from the unit circle that the sine is the y-coordinate and it's radical 2 over 2 here and over here. So that would be pi over 4 and 3 pi over 4. But the one that's in the zone is pi over 4, so that's my answer. Over here, let's say that I would like to find the arc cosine of negative 1/2. In order to find the arc cosine, I'm saying where is the cosine negative 1/2? Now the cosine, you'll remember, the cosine is the x-coordinate, and the x-coordinate is negative 1/2 here and here. Because remember, I've got my short, long. So the coordinates of this point would be negative 1/2, comma, radical 3 over 2. The point down here would be negative 1/2, comma, negative radical 3 over 2. So the cosine of both of these is negative 1/2, but the only one that's in the zone is the one up here, which is 2 pi over 3. So instead of using 4 pi over 3 down here, I would use 2 pi over 3. Okay, let's do one more. Let's say I'm asking you to find the arctan of negative 1. So I'll write that the other way. Arctan of negative 1. In other words, where is the tangent negative 1? Now, we know that when we're figuring out tangent, that's sine over cosine or y over x. Now the only places where the tangent is 1 or negative 1 is going to be at the pi over 4 angles. More exactly, if I want the tangent to be negative 1, that's going to happen here, and it's going to happen here. This is 3 pi over 4, and this is 7 pi over 4. Now, even though the 7 pi over 4 is in the zone, you cannot write the answer as 7 pi over 4 because the answer has to be between negative pi over 2 and positive pi over 2. So instead of writing it as 7 pi over 4, write it as negative 1 pi over 4. Look at it as a negative rotation. So the answer to this one, using the number that's in the zone, is negative pi over 4. A couple things you'll have to do on your test. One will be to take an exponential equation and write it in logarithmic form. And if we do that, you just need to remember the base of the exponent is the base of your log. So I'm going to have log base 3. Now, the log of a number is the exponent I put on the base to get the number. The log always equals the exponent. So the other place left would be right here. Over here, because there's no number written here, we know that this is a 10. Now the base of the log is also the base of our expression. So 10 to the x, because the log equals an exponent always, that would have to be 9.8. You'll need to be able to go back and forth between the two forms. Okay, let's say that I tell you that the log of 2 is 0.3 and the log of 3 is 0.5. And given that knowledge, you have to find the log of 6 and the log of 800 without using a calculator. If you have to do that, you're going to have to use your laws of logs. Remember that the log of 6 could also be thought of as the log of 2 times 3. And our law of logs says that if you have the log of a product, it can become the sum of the two logs. So if I add the log of 2, which is 0.3, plus the log of 3, which is 0.5, I get an answer of 0.8. Now the second one's a little trickier. Let's see what we can do here. The log of 800 would be the log of 8 times 100. So let's see what that looks like. That would be the log of 8 plus the log of 100. Now, neither one of these are 2's or 3's. However, I could write the log of 8 as the log of 2 cubed, and I can write the log of 10 as the log of 10 squared. Now, this 3, because it's an exponent, can come down front, and I have 3 times the log of 2. I can do the same thing here. I can bring the 2 down, and I get 2 times the log of 10. Well, you should know that the log of 10, because the base is 10, and when the base is 10 and the number is 10, the log is 1. Because the exponent that I put on 10 to get 10 is 1. So this becomes 2 times 1. Over here, this becomes 3 times the log of 2, which is 0.3. So 3 times 0.3 is 0.9, plus 2 times 1, which is 2. This answer turns into 2.9. So take the numbers that you're given and see if you can write them somehow in terms of the numbers that you're given here. Alright, let's look at a couple more problems with the same given logs that might be a little on the tricky side. If you have the log of a radical, just remember that radicals or square roots are the same thing as using an exponent of 1/2. If you can write it with an exponent, we have the rule that says that can come down front, and it becomes 1/2 log of 3. Now, I know the log of 3 because it was given up here. The log of 3 is 0.5. So 1/2 times 0.5 would be 1/2 times 1/2, which is 1/4, or 0.25. Over here, the log of 1.5 doesn't seem to use a 2 or a 3 unless you look at it as being the log of 1.5, which is 3/2. Because if it's written as a fraction, then I can change it to the log of 3 minus the log of 2. I know the log of 3 is 0.5. The log of 2 is 0.3, so when I subtract them, I get 0.2 as my answer. So anytime you see a square root or a cubed root or any other root, write it as an exponent so that you can pull it out down front from the log. And if something looks like it doesn't work with what you have, see if you can represent it another way. Okay, one of the things we do with our laws of logs, or our properties of logs, is to expand expressions and to contract them and write them as a single log. So first of all, let's look at expanding them. And I'm just going to go over this. We've done this in class, but remember that exponents come down and products turn into sums. So this would become the log of x squared plus the log of y. And because we have an exponent, the 2 will come down front, and I get 2 log x plus log y. Now this one's interesting because it's got a radical. We just did one like that. Take that radical and write it as a power of 1/2. Now, the 1/2 will come down, and I get 1/2 times the log of all of that stuff. Well, that's the log of a quotient. So that's going to become the log of x minus 2 log y minus log z. The reason is anything that is coming from the numerator becomes a log that's being added. Anything that comes from the denominator becomes a log that's being subtracted. And then I also took this exponent and put it down front. Now, you can leave it like this, or you can multiply through by the 1/2. Doesn't matter. Both of them are acceptable. Just remember that anything that's being multiplied in the denominator will be subtracted when you expand it. Anything that's being multiplied in the numerator will be added. And any exponent that's on the entire quantity, including if you have a fractional exponent, it will be pulled down front. Okay, now let's go the other way. All right, the first thing we need to do when we are asked to write an expression as a single log is to look at any numbers that we have in front, because they should go back up as exponents. The 5 goes up here, the 6 went up, and this is not a number being multiplied in front of ln. It's not an exponent, but this one is. So once you get the exponents put back, then you can look at the sums and differences. So in this case, look for the ones that are positive. That would be the first term and the third term. So when I write my single expression, I have ln, and then in parentheses, I'm going to make a fraction, because anything that is positive came from a product in the numerator. So that means I've got a y to the 6th, and I've got a 2. So I think what I'll do is, instead of writing y to the 6th times 2, I think I'll just write 2 y to the 6th. And then I go look at all of the terms that were being subtracted, because terms that are being subtracted came from the quotient. So my x to the 5th, w to the 3rd would go in the denominator. Okay, now for this other one, I need to do the same thing. Anytime I have a number out front, I need to put it back up as an exponent. So now the 3 is no longer in front, it's an exponent. Now I can take this, and before I do anything with the 1/2, take a look at what you have here. I've got a sum of 2 logs. Well, that turns into the log of the product, x, y cubed. Now, that's still in brackets. I've got a 1/2 out front. Anytime you have a number out front, we're going to do what we were doing before. That comes out, and it goes up as an exponent on the entire expression. So I have a 1/2 on the entire expression. So what that ends up looking like is the log of xy cubed, that whole quantity, to the 1/2. At this point, I could have left this bracket off and this bracket off, because I just had 1/2 times the log of that quantity. The 1/2 goes up, so once I've put it up there, I can take it off, and I have log of xy cubed to the 1/2. And then to finish the problem, whenever you have a 1/2 exponent, that's the same as a square root. So a 1/2 exponent becomes the square root. Okay, let's solve a couple equations. When you solve equations and the variable is embedded in the exponent, you either have to solve it as an exponential equation or using logs. If your two bases can be written with the same base, then you can do it using exponential equations. So when I look at 27, I know that 27 is 3 times 3 times 3. In other words, it's 3 cubed. I know that 9 is 3 squared. So when I look at this equation, the 27 became a 3 cubed, and then that's raised to the 2x plus 3 power, and that equals 3 squared. So, continuing to solve this, when I have an exponent raised to an exponent, that becomes 3 to the 3 times 2x plus 3. We multiply the exponents. Over here, I'm just going to leave it as 3 squared. So this exponent becomes 6x plus 9. This one is still a 2. And whenever you have an equation where the base equals the other base, that means if 3 to this stuff equals 3 to the second, what must be true is that 6x plus 9 must equal 2. And when you solve this, 6x equals negative 7, so x equals negative 7 over 6. That would be the solution. So if you have two numbers and the bases can be written to be the same base, in this case it was 3, all you need to do is get single expressions and then set the exponents equal to each other. Okay, here's an example of a problem in which you cannot make the bases the same, because 5 and 42 cannot be written with the same base. If that's the case, then you need to use logs to solve it. So, to do that, what you need to do is take the log of both sides, and frankly it doesn't matter if you use the natural log or the common log. I'm just going to use the common log. I'm going to take the log of both sides. So I'm taking the log of this quantity and the log of this quantity. So now on the left, because this is an exponent, I can bring it out front. So what I end up having is the log x times the log of 5 equals the log of 42. Now if you were doing this on your calculator, you could go ahead and fill this in with a number and fill this in with a number and solve it. On your test I'm going to ask you just to leave it in terms of log, and so that means all you need to do is divide both sides by the log of 5. Your final answer would then be x equals the log of 42 over the log of 5. And while we're at it, if you end up with something like the log of 20 over the log of 30, don't you dare think that you can simplify that into 2/3 or anything else. Remember from when we talked about trig functions, this is an entire quantity. You cannot pull out the 20 or do anything else with the 20, and this is an entire quantity. Same as this is over here. Don't take the log of 42 and divide it by 5 or anything else. And also, this, sometimes people will take this and they'll think that because it's division, they'll think it's the log of 42 minus the log of 5, or sometimes people will think it's the log of 42 minus 5, but none of those match the rules that we did before. If you have the log of a quantity divided by the log of a quantity, you have two choices. You either leave it alone in terms of log, or you put those two logs in your calculator and come up with decimal numbers. So for this problem, and the one that's similar to it on the test, you're told to leave logs in your answer, which means leave it in this format. If you have the variable in your base, then what you might want to do is write it in exponential form. X to the 1/4 equals 3. Now remember, a 1/4 as an exponent is the exact same thing as a fourth root. So if I want to undo a fourth root, then I need to multiply both sides, or actually take both sides to the fourth. So on the left side, these undo each other and I just get an x. On the right side, 3 to the fourth. 3 times 3 is 9, times 3 is 27, times 3 is 81. So x would equal 81. Okay, here's one last problem. When I look at this, I see my variable is embedded in this log. But I don't have just log equals log, so that's a little bit tricky. One thing I might want to do is stick this 3 back, because if I do that, then I have the ln of x cubed plus the ln of 5 equals the ln of 320. But I still, in order for me to say, like if I had the ln of x equals the ln of 3, if I have log equals log, then I can say the argument equals the argument. But I don't have that. I've got the sum of two logs equals a log. But wait, don't I know how to take the sum of two logs and combine them? I can take these two and write them as a single log. Then I would have ln of 5x cubed equals ln of 320. If you can get it to be the log of some stuff equals the log of some stuff, these two quantities must represent the same number. That's the only way that those two logs can be equal. So that means I must have 5x cubed equal to 320. So to finish the problem, let's just divide by 5, and I get x cubed equals 64, and the number that I would cube to get 64, in other words, the cubed root of 64 is 4, because 4 times 4 is 16, times 4 again is 64. So the solution would be x equals 4. So if you can get an equation to either have the same base, like if I have something like this, then I can set the two exponents equal to each other and solve. Likewise, if I have two logs, like the log of 2x equals the log of 11 or something like that, if I have the logs equal to the log, then my arguments must be equal, and I can set the two arguments equal to each other and solve. So if you don't have that, then you have to either try and get it like we did here. We combined it so that I got log equals log, or over here, if the bases are not the same, then you would take the log of both sides. Okay, so if you can do the problems that or understand and could replicate the problems that I put on this video, you should do just fine on the test. You need to change logarithmic expressions to exponential, exponential to logarithmic. You need to expand log expressions using our laws of logs. You need to contract them and write them as single logs, and you need to be able to solve equations that have your variable as part of a log. The base of the log could be the base of an exponential expression, could be the exponent of an exponential expression. So wherever that variable is, you now have the tools to either solve it with logs, get the bases the same, or change the expression into the other type of equation so that you can work on it and solve it. There will be a couple matching problems on graphs, so you should probably take a look at that. I showed you the log graph, but make sure you're also familiar with exponential graphs. For example, something like y equals 2 to the x. What does that look like? What does the arcsine graph look like? And the other trig functions. And then I showed you what a basic log graph looks like. But you're going to have a matching section on these types of graphs. So make sure you're just familiar with those. Other than that, you should be well prepared, and good luck.